All right, something similar, a little easier, but with a couple of wrinkles here in terms of solving this polynomial inequality. So here it says solve the polynomial inequality and graph the solution set on a real number line. Express the solution set in interval notation. Okay, so a few things worth noting right off the bat. Number one, they've already done us the favor of factoring this polynomial down. Okay, so if you recall in this problem that we were talking about previously, part of finding the solution set is finding the zeros so that we could then set up these intervals that we could test with these values. Okay, and again, let's take graphing off the board, but we cannot ignore this material over here. Okay, we may not want to graph it, and again, I'm just saying we want to be more well-rounded. Can we graph this? Can we graph this inequality right now and solve this? Probably. But let's challenge ourselves. Let's look at it from the eyes of an algebratist. That's a word. I just made it up. I think. I don't know. A geometer, is that somebody who does geometry? An algebratist, an algebrometer, something that measures algebra. I don't know. You guys figure that out. Okay. Get back to me on what we would call someone who does algebra, right? Um, an algebran, like a surgeon does surgery, like an algebran. I don't know. Anyway, you guys figure that out, okay? So they've done us the favor of already factoring this. And part of this process is finding the zeros. We want to know where it's less than, we want to know where this function is less than or equal to 0. And even if we didn't want to know where it was equal to 0, we'd still want to know where it was equal to 0, because then that would separate our intervals, and then we'd want to find where the values are less than that, right? So let's look at what zeros we do get from this. We get x equals 0 here. This one's a little tricky, right? We have 4 minus x. What's the 0 here? If we subtract 4 from both sides, then we'd have to multiply by 4, or excuse me, by -1, or divide by -1. So this one is actually 4, and then this one here is the 6 that we get, right? Since all of these are first degree values of x. All right, so here are our 3 zeros. All right, so after we do this, and again, if we're strictly looking at this from the standpoint of graphing, okay, we then take, or not graphing, excuse me, we take these zeros and we separate the domain into these intervals. So we go from negative infinity to the first 0, which is 0. Okay, there's our first interval. So again, why am I doing this? Because once you get to 0, okay, this graph crosses the x-axis. So part of the graph on the left side of 0 is either above or below. And then once it crosses the x-axis at 0, it has that opposite behavior, right? Think about that for a second. This still, and we didn't even talk about this in the previous video, but this is also talking about the multiplicity, isn't it? Okay, this has a multiplicity of 1, right? It only happens one time, so that means we know that the graph crosses at that value. So that even draws on our understanding of multiplicity. If this was x squared, we'd have a different discussion, right? Because we would know that it bounces at 0 and doesn't necessarily cross. So that's something worth noting, right? We spent some time when we were doing the fundamental theorem of algebra of graphing, right, by hand, just drawing sketches of these polynomial functions just based off of zeros and behavior, right? Leading coefficient, degree, multiplicity, all of that still plays an effect on what we're doing here. So from negative infinity to 0, then we pick up at 0, go to the next 0 value, which is 4. And then we have another interval which goes from 4 to 6. And then we have another interval which goes from 6 to positive infinity. Okay, so again, at each one of these values, and I'm fighting the urge to draw a graph, right? Okay, but at each one of these values of x, the function equals 0. So within these intervals, that graph is either crossing and going above or crossing and going below until it gets to the next 0, right? Again, all of that depends on degree, end behavior, leading coefficient, multiplicity, all the stuff that we've discussed. But if we just want to take a numerical or algebraic approach to this, we know that this graph is either below the x-axis on the left side of 0 or above it? Let's figure out which one it is. If I plug in, and I gave you this example in a previous video, I can plug in any number that falls in this interval, and it's either going to be greater than or less than 0. I can pick anything. I can pick -1. -1 would be fine. But I'm going to use my brain power to work with big numbers and sort of cheat through this, right? Let's make this -1 million. Let's make x -1 million. If this is -1 million, this number is negative, right? So I'm taking this number and it's incredibly negative. If I put -1 million here and I subtract -1 million from 4, this number is incredibly positive, right? If I put -1 million here and subtract 6, this number is extremely negative, -1 million and 6, right? So now I'm taking a negative million, multiplying it by positive 1 million and 4, and then multiplying that times -1 million and 6. What's a negative times a positive times a negative? It's positive, right? So this is actually greater than 0, which is not what I'm looking for. Cross it off, right? I want numbers that are less than 0. So from this point forward, I feel like you can see where this is headed, okay? But in case you can't, let's because again, based on this idea of multiplicity, you might see where this is going, but if you don't, let's test. Now we need a number between 0 and 4. I can't use 0, I'm not going to use 4, so let's use something easy. Let's use 1, right? If I put a 1 in for x, and I put a 1 in for x here, and I put a 1 in for x here, what do we get? We get 1 times 3 times -5. 1 times 3 times -5 is -15, which is less than 0, right? Which is what we want. We want an interval that's less than 0, so we're going to use this one. Now let's choose a number between 4 and 6. Okay, what's a number between 4 and 6, right? 5. So if we put 5 in, then we put a 5 in here, then we put a 5 in here, what happens? We get 5 times -1 times -1. What's 5 times negative times a negative? That's positive, which is greater than 0, which is what I don't want, right? Now let's choose a number over here, like a million. What happens if I plug a million in? Or 1,000, million, whatever you want. If I put a million here, that's 1 million. This number, if I subtract a million from 4, okay, and then if I subtract a million from 6, what happens? What is this? Very positive. What is this number? Very negative. What is this number? Positive. Because we're only subtracting 6 from a million. What's a positive number times a negative number times a positive number? That's negative, which is less than 0. So earlier, okay, that's a check mark. That's a poorly drawn, quickly drawn, poorly check mark. So what I mentioned earlier when I said you might be able to see where this is going, right? What did we say? At each one of these values of x, the graph is crossing the x-axis. So now that the cat's out of the bag here, let's talk. So this graph crosses the x-axis at 0. It crosses the x-axis, we'll put 4 here and 6 here, okay? Now, what is the degree of this function? The degree of this function is 1, 2, 3 values of x, so it's x cubed. So I'm beginning to know what its end behavior is going to look like. What's the leading coefficient? And I don't even need to know specifically what the leading coefficient is. I just want to know, is it positive or negative? Well, if I multiplied all of this out, what would happen? I'd do x times negative x at some point, which is negative x squared, and then I'd multiply that times this x. So the leading coefficient is negative. What does that tell me about this function? That tells me its end behavior looks like this, right? And again, this all goes back to what we were talking about before, about end behavior, leading coefficient, degree, all of that stuff. Now here, okay, we know that the multiplicity of this 0 is 1, so we know that the function has to cross, right? And if it has to cross there, and the multiplicity of this 0 is also 1, I know that at some point it has to come back up at 4 and cross because it has a multiplicity of 1. Then it has to come back down to cross at 6, and it's going to keep going. So here's the end behavior. that we know based on degree and leading coefficient, okay? Where is this, and this is getting kind of drawn over a lot, but where is this entire function less than 0? Being less than 0 is below the x-axis. So where is this function below the x-axis? Right here and right here, right? And those are the two intervals that I found algebraically by testing, between 0 and 4 and values greater than 6. All right? So they wanted me to express this in interval notation. I'm using brackets for these. Why am I using brackets? Because of the line that's underneath, right? The line that was underneath here tells me it can be equal. So this is our interval notation. On a number line, here's 0, here's 4, here's 6. On a number line, it would look like this. We're still using the brackets. We're shading like this. We're still using this bracket, and we're shading like so.